Lattice enthalpy. Okay, right, this topic has got a lot of definitions. I'm going to go to the definitions quite quickly, but you can always look up the definition. Okay, first, the definition of lattice enthalpy. So lattice enthalpy, so the symbol is a standard enthalpy change. That's the symbol that we use. Standard enthalpy change for lattice enthalpy is the enthalpy change when 1 mole of an ionic compound, lattice enthalpy is the enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions under standard conditions. And when we say standard conditions, we mean 298 Kelvin, 1 atmosphere, or 100 kilopascals. Okay, right, so the marking points for this: enthalpy change when 1 mole of an ionic compound is formed from its gaseous ions, under standard conditions. Right, so let's have a go at it. If you're asked to write an equation to represent the lattice enthalpy of sodium chloride, write an equation to represent the lattice enthalpy of sodium chloride, what would you write? So it is the formation of 1 mole of ionic compound. You do not put a number there. Do not write a number there, because it's the formation of 1 mole of ionic compound from its ions in the gaseous state. So it's really important that they're in the gaseous state like that, okay? So that's an equation to represent the lattice enthalpy of sodium chloride. Now, you are not expected to know the specific values, but you should know whether it's going to be positive or negative, this enthalpy change. So is this is it going to be positive or negative? And then you say to yourself, well, a bond is being formed. Forming a bond is negative enthalpy change, exothermic. So these values are also going to be negative. Let's have a go at potassium chloride. If you were to write an equation to represent the lattice enthalpy of potassium chloride, KCl solid from its gaseous ions. Right, again, you should recognize that it is exothermic because it's forming a bond. Forming a bond releases energy. You should be able to work out the relative magnitude, the size of these values, okay? So if they tell you that this one, for sodium chloride, for example, sodium chloride is minus 781 kilojoules per mole. Okay, that's the value for sodium chloride. But relative, what's the value for potassium chloride going to be? Is it going to be more negative? Is it going to be something like, minus 850 kilojoules per mole? Or is it going to be less negative? Is it going to be something like minus 700 kilojoules per mole? So you should be able to say, relative to that value, what's potassium chloride going to be? Okay, now the way you work this out, if you take this top one, if you take sodium chloride, for example, all right, sodium chloride, if you turn around this equation, round, that's talking about breaking up sodium chloride. So breaking up sodium chloride, okay, if you want to break the bond, breaking sodium chloride, okay, that's going to need 781 kilojoules, okay, if you turn it around. So basically, lattice enthalpy tells you about the strength tells you about the strength of the ionic bond. Okay, because if I want to break it up, I'm going to need 781 kilojoules to break it up. Okay, so let's look at potassium chloride. Is potassium chloride going to be easier to break up or harder to break up? Well, the only difference here is the size of the ion. So Na plus is smaller than K plus. Okay. The chloride is the same size for both of them. The chloride is the same size for both of them. This chloride is the same size, yeah? But the K plus is a larger ion. The K plus, because it's larger, is not going to have a very strong attraction with the chloride ion. Larger ions cannot pack as close together. So K plus is a weaker attraction, and therefore it's a weaker ionic bond, and therefore it's more easily broken up. Okay, so let's just write this down. So I'm going to write down Na plus is smaller than K plus. Okay, therefore Na plus has a stronger attraction to Cl minus than K plus. Therefore, there's a stronger ionic bond. There's a stronger ionic bond between Na plus and Cl minus compared with K plus and Cl minus. Compared with K plus and Cl minus. Okay, so sodium chloride has got a stronger ionic bond, therefore more energy is needed to break it up, therefore more energy is released when the bond is formed. Okay, so which of these is going to be correct? It's going to be the one with the lower, less exothermic. Okay, the value is actually minus 711 kilojoules per mole for potassium chloride. So less energy is released when this bond is formed, because it is a weaker ionic bond. It's a weaker ionic bond because the attraction is not as great, because K plus is larger. Okay, really common mistake is that people talk about atoms, but you're not to talk about atoms, you've got to talk about ions, the attraction between the ions. And just to say one more time, you don't have to remember specific values, but you should be able to work out relative values, whether it's going to be more exothermic or less exothermic. Okay, one more example is magnesium. Well, actually, let's do sodium first. Okay, let's do one more example. We'll move on. So if you write an equation to represent sodium oxide, the lattice enthalpy of sodium oxide. Okay, sodium oxide, that's sodium oxide. From its ions in the gaseous states, you've got 2 sodiums, you need to put 2, plus oxide ion, like that. Okay, what's the value for the lattice enthalpy going to be? Well, it's definitely going to be negative, right? It's definitely going to be negative because you're forming an attraction. If sodium chloride, the one for sodium chloride was minus 781. So what's this one going to be for sodium oxide relative to sodium chloride? Is it going to be more exothermic? Is it going to be less exothermic? Right, the difference here, the sodium is the same size, the sodium ion is the same size for both of them, but this time you've got an oxide, and the oxide ion is small and highly charged. Yeah, it's highly charged and smaller than the chloride ion. Okay, so it's highly charged. So therefore there's going to be a stronger attraction. And it's actually minus, for sodium oxide, it's minus 2,521 kilojoules per mole. So it's a really strong ionic bond. A lot of energy is released when it is made. A lot of energy will be needed to break it up. So the more highly charged, the smaller the ions, the stronger the bond. Okay, and it's similar. If you take MgO, for example, that will be even stronger because it's a 2 plus ion and a 2 minus ion, and it'll be even stronger. Okay, so that's first for lattice enthalpy. Next thing for lattice enthalpy is you cannot determine lattice enthalpy directly. Okay, where do they get these values from? Where do these values come from? Okay, lattice enthalpy, I'm just going to write LE for lattice enthalpy. Lattice enthalpy cannot be measured directly. Sorry, the pen's cutting out. Lattice enthalpy cannot be measured directly because it is impossible to form 1 mole of an ionic solid, 1 mole of an ionic solid from gaseous ions. Okay, it's impossible to do. So therefore we use an enthalpy cycle. This is from AS. So we use an enthalpy cycle in order to determine the value. Okay, and the enthalpy cycle is quite specific. It's called a Born-Haber or Born-Haber cycle to determine lattice enthalpy. Okay, so I'm going to show you how to draw a Born-Haber cycle. Okay, you need a big piece of paper. All right, so let's do magnesium chloride. Okay, so a Born-Haber cycle. So we're going to write a title here. So Born-Haber cycle, or Born-Haber cycle to determine the lattice enthalpy of magnesium chloride solid. Okay, now what we need to do is we need to start at the bottom. So this is an A4 piece of paper. I'm going to start quite way down the bottom. I'm going to start down here on the right hand side, and I'm going to draw magnesium chloride. So it's just an enthalpy cycle, solid state. Okay, and then I'm going to draw from the gaseous ions, so can you see that? From the gaseous ions plus 2Cl minus gaseous. Okay, that is lattice enthalpy. Okay, we stand lattice enthalpy. Now when you draw a Born-Haber cycle, when you go up, that is endothermic energy needed, and when you go down, the arrow goes down, that is exothermic energy released. Okay, so I'm going to build it up slowly. That is what we're trying to work out. We don't know what it is. Okay, don't know what it is, and we're going to determine it using a cycle. All right, the next thing we're going to do is we're going to start just a little bit up on the left, I'm going to start with the elements in their standard states: magnesium solid and Cl2 gas. Okay, the elements in their standard states, and that is called, going from the elements in their standard states to that is called enthalpy change of formation. Okay, so do you remember the definition for formation? Okay, formation is the enthalpy change. Let's quickly write this down. Formation is the enthalpy change for the formation. Do you remember from me last year? For the formation of 1 mole of compound from its elements from its elements in their standard states. Sorry, my writing is terrible. In their standard states. Okay, and that is formation. You can always look these definitions up. Formation, alright? Then what we're going to do, we're going to go one step at a time. And the first thing I'm going to do is turn the magnesium solid into magnesium gas. Because what we need to do is we need to end up looking like that. So we go from the magnesium solid to the gas. Now that is called atomization of magnesium. Okay, you need to know the definition for atomization. Okay, for atomization. Let me just write atomization there as well for spelling. Atomization, which is all one word. Okay, that's the enthalpy change. Enthalpy change for the formation. Enthalpy change for the formation of 1 mole of gaseous atoms. 1 mole of gaseous atoms from the element in its standard state. Okay, so it's for the formation of 1 mole of gaseous atoms from the element in its standard state. Okay, now the chlorine, nothing has happened to the chlorine, so we just carry it exactly the same. Okay, right, and what we're trying to do is turn this into this. That's what we're trying to do. Okay, next thing we're going to do is with the magnesium, we're going to go magnesium, we're going to remove an electron. Okay, so still in the gaseous state, Cl2 gas, and there's the electron. Okay, do you remember what that's called? That enthalpy change is called? That enthalpy change is called ionization energy. So I put IE1. First ionization energy. First ionization energy is the energy required to remove the first electron from each atom in a mole of gaseous atoms in the standard state. Do I need to write this down? Oh my gosh. Alright, ionization energy 1 is the energy change, energy required, or energy needed, or energy change to remove the first electron, from each atom in a mole of gaseous atoms to give a mole of gaseous ions, etc. Okay, etc. The mole of gaseous to give a mole of gaseous ions. Okay, first ionization energy. And then can you see we're trying to go to there? So we need to do it again. We need to go, take another electron. Don't forget your state symbols, you will lose a mark. If you miss one state symbol, you'll lose a mark. Nothing has happened to the chlorine. 2 electrons now, because we've removed 2 electrons. So that's the second ionization energy, IE2. Okay, now the magnesium is sorted. Can you see it's in exactly the same, what we want it to be, right? Now we need to work on the chlorine. Now the first thing we're going to do with the chlorine is the magnesium is the same, we've sorted that out. We're going to turn the chlorine from a molecule to gaseous atoms. Okay, to gaseous atoms, and that is called atomization of chlorine. Atomization of chlorine. Okay, now the definition for atomization. Atomization is the enthalpy change for the formation of 1 mole of gaseous atoms from the element. Can you see we're forming 2 moles of gaseous atoms? So we need to times this by 2 because we're forming 2 moles of gaseous atoms. Okay, so whatever that value is, we need to times it by 2. Okay, now the last step to link this whole cycle together, because a cycle has to be continuous, like a cycle, yeah, is we're going to go from here, I'm going to draw an arrow down to here to link this cycle together. And can you see what is happening here? We've got 2 Cl's and we've got 2 electrons. we've got 2Cl minus, yeah? So an electron is going into Cl, an electron is going into Cl, okay? This is called electron affinity, okay? EA, okay? It's called electron affinity. And the definition is really similar to ionization energy, okay? Is the energy, so let me just squeeze it on the bottom. Sorry, the writing's going to be really terrible. Squeeze it on the bottom, okay? So electron affinity is the enthalpy change when one electron is added, not removed, but is added to each atom in a mole of gaseous atoms. In a mole of gaseous atoms. Okay, enthalpy change when one electron is added to each atom in a mole of gaseous atoms to form a mole of gaseous 1- ions, which I can't fit on the piece of paper. Okay, it's called electron affinity. But it has happened twice because there are 2 Cl's, so we need to times that value by 2. Okay, now that's how you build up a Born-Haber cycle, right? What you would do, and if you're doing this in a question, you'd actually write the energy by the side. You write the enthalpy change by the side, but I haven't got the specific figures for this. Okay, now we want to find the lattice enthalpy. That's the job. Okay, so we want to find this, and this is the start and this is the end. Oops, sorry, this is the end. This is what we want to find. We want to start here and we want to go down here to the end. Now this is using Hess's law. Do you remember this from last year? Hess's law. Enthalpy change is independent of the route taken. Enthalpy change is independent of the route taken as long as you start and you end at the same place, yeah? So you start and the end at the same place. So we're going to start here, right? And instead we're going to go round here, round here, round here, round there, and end. We're going to go that direction instead. We're going to start here, and that is the same as going down here. So we're going to go up electron affinity. Arrow's going in the wrong direction. We're going up electron affinity, so we need to change the sign. So we need to go minus 2 times electron affinity, because we've got 2 of them. And we're going to go down here. That arrow's in the wrong direction, so we need to go and minus 2 times atomization of chlorine. And the arrow's going in the wrong direction, so we need to go minus second ionization energy. And we need to go down minus first ionization energy. And we need to go atomization of magnesium and minus. We need to change the sign, magnesium. And then finally, this one is in the right direction, so we just keep it. And delta HF formation. Okay, but it's the idea, it's a cycle. Now you can approach this in different ways, but as long as you're trying to find the start and the end, and you can go around that direction. But there are other ways to do it, and that will give you the answer. Okay.